when we have a derivative, we usually say y prime is our most common, but we use that Leibniz notation too a lot, dy over dx. Well, it turns out dy and dx, they are also given a name. And the name of those things, they're called differentials. If we break them apart, essentially, break those apart, dy and dx are called differentials. So separate them out, instead of having dy over dx, separate them out, make them separate quantities, if you will. So the parts there of our derivative, if you will, notation, are called differentials. Now, here's what these mean, or one thing we can think about them meaning. Well, dy is usually thought of as a function, if you will, of dy is a function of dx. What I mean is, usually we write dy in terms of dx, and really, dy over dx, that's equal to our, if we're talking about function f, it's f prime of x, and those two correspond. If you solve that for dy, that gives us a relationship, and we can do that. That gives us the relationship between dy and dx. If I just multiply both sides by dx, don't I get this? Yeah. That's our dy equation. dy is equal to f prime times dx. So I might say, that's great. Well, that comes in handy. We'll use that different places along the way in in our discussions, and then if you take further calculus classes and other math classes and other places, but you'll use that quite a lot. That little equation is kind of handy. Now, here's so that's what it equals. It's not hard to compute. So if so, find dy for f of x equals square root of sine of x. Well, dy is equal to f prime of x times dx. So dy would equal, you just have to do the derivative times the dx. Well, you get the derivative here. Let's think of this in terms of sine of x to the power, right? Square root of sine of x is sine of x to the 1/2. So the derivative is going to be 1/2 times sine of x to the minus 1/2 times the little chain rule, right? Derivative of the inside then, that's the derivative of the outside, so the derivative of the inside times cosine of x. That's my derivative. Multiply that by dx, ta-da. Okay. So, just a little formula, but it's a fairly easy one to understand, I think. Now, what about the meaning of differential? Well, again, think of dy over dx, that's the derivative, right? What does the derivative give me? It gives me the slope of the tangent line, right? At a particular value. Well, if dy over dx equals the slope of the tangent, another phrase or another way we know a slope is rise over run. That's what slope is. guess what you can interpret dy as then? It's the rise of your slope of your tangent line, and dx is the run of the slope of your tangent line. Yeah, dy is the rise, dx is the run, right? Rise over run. Okay, so here's a graphical interpretation. Say I've got this function here. Find f of x. And I'm talking about this x value here. So that's corresponding to that point. All right, so I've got this tangent line here. Well, so what have I got as far as dy over dx? And we've looked at coming up with this slope different ways, but let's just say we do this. Just kind of and they'll usually give us this this run here for us, the dx in other words. Yeah, so that if I go from this point up to this point on the tangent line, dx is the run, dy is the rise, so that's dy here. With me there? Like I said, they will usually give you this dx, how far dx is, and so the dy corresponding is just that rise to that tangent line. Right? Because that's the run, that's the rise. That's the meaning of dy dx if you look at it on the graph there. Okay? Now, what they also throw in here to the mix are a couple of other quantities. It's kind of for comparison. They also talk about delta x and delta y. Those you may be more familiar with the deltas. Delta x, change in x. And delta y is a change in y. Now, important to note here, when I'm talking about the change in the y value, isn't that the change in the function value? It's the change in the function value. So going back to my picture here, comparison's sake, all right, so I went over to this much and then went up. So is it from here to here, which would be interpreted down here, to this x value? Wouldn't that be my change in x? Yeah, delta x. So I'm going from this x to this x. That's the change in the x. Well, do you notice anything about the change in x and dx? Dx is from here to here. Wouldn't that be the same as? They're the same, okay. Yeah, delta x and dx are going to be exactly the same. However, on the change in y, what do you see about that? Well, the change in y, okay, so I go to this point, up to this point, my y value is over here. So that's, call it y1. And then I go from this point, I go up, what's the y value at this point? Well, I don't go up all the way to the tangent line. I'm talking about the y value, the function value. And so the y value I'm talking about here is actually this y value. So the change in the y value is the difference between y2 and y1. Based on my picture there. But let's think about that a little more. How do I get y2? Well, y2 is the y value at this x value. And what is this x value? Well, if this is x, then wouldn't this be x plus delta x? Isn't that the x value here? So the y2 value is the y value at x plus delta x. Or in other words, f of x plus delta x. It's the function value at this, right? It's the function value evaluated at this x. The y1, a little easier. The y1 is this value associated with this, so it's the function value at x. And so this is our change in y or delta y formula. And we're going to use that here in a second too. This is dy formula and that's delta y. Now, we've already mentioned delta x and dx are the same. Is that true about dy and delta y? Are those going to be the same? Those aren't going to be the same, are they? Because here's dy, where's delta y? Delta y is the difference between the two function values. So isn't delta y this amount right here? It's the difference between those two. Changing the y's here. So dy goes from here to here. So it's a little bigger in this case. It may not be bigger, it may be smaller, but they're going to be close to one another, but they're not going to be the same. Dy and delta y are going to be just a little bit different. Okay? But dx and delta x, those are exactly the same. All right. Well, let's just compute a couple of these. And then. All right. So let's for f of x equals x cubed minus 3x squared plus 4. Evaluate dy and delta y for x equals 1 and dx equals 0.5. So we're just going to compute those two things. And again, those are just formulas, not, you know the formula, it's nothing terribly difficult. Dy is f prime of x times dx. So dy in this case would be, all right, so f prime would be 3x squared minus 3x squared minus 6x times dx in this particular case, right? Because that's the derivative. F prime is 3x squared minus 6x. All right? And so in this particular case, it wants me to evaluate a specific value of this. When x is 1, dx is 0.5. So dy equals, plug in x to be 1, and dx to be 0.5. So we got dy is 3 minus 6 times 0.5. So it's negative 3 times 0.5. Is that negative 4.5? I think that's negative 4.5. Believe that? Did I do that right? All right. So now delta y, here's our delta y formula right here. Delta y equals f of x plus delta x minus f of x. That'll give me my delta y. Oh, I do that wrong. That's not negative. 3 times, I don't know what I was multiplying. 3 times, negative 3 times 0.5 is negative, it's just negative 1.5. I don't know where I got negative 4. Sorry about that. I don't know what I was multiplying. Okay. So dy is negative 1.5. Delta y, on the other hand, here's how we compute it. It's f of x plus delta x minus f of x. I've got the x. Didn't specifically state delta x, though, in the problem. However, what do you know about delta x? Same as dx, right? Delta x equals dx, so if dx is 0.5, delta x is 0.5. So I've got delta y is going to be f of x plus delta, that'd be f of 1.5 minus, and then just f of x, dx is 1, so it'll be f of 1. So it's just computing the function value at 1.5 and then subtracting. So f of 1.5 would be, just go back to the original equation here, so it'd be 1.5 cubed minus 3 times 1.5 squared plus 4. Definitely not going to trust myself. Anyway, multiply. All right, so 1.5 cubed minus 3 times 1.5 squared plus 4, I get 0.65 for f of 1.5. And then minus f of 1, so f of 1 is just 1 minus 3 plus 4. So that's 5, it's 2. So f of 1 is 2. And then 0.625 minus 2 is negative 1.375. Yeah, that again confirms these aren't going to be equal. They should be close unless you choose a large delta x or dx. They're going to be close because little gap there. All right. Let's do another one, then we'll look at the graph. Graph to that as well. Is this okay? I think I got it finally right. I don't know where I got the 4.5. Times your mind does tricks. All right. Let's see. Yeah, all right, so compute delta y and dy. For f of x equals x squared plus 5x minus 6. At x equals 2, with delta x equals 0.1. All right, so I listed delta y first here, so let's do delta y first. Delta y is f of x plus delta x minus f of x. So delta y here would be f of, the x is 2, the delta x is 0.1, so x plus delta x would be f of 2.1 minus f of x, so f of 2. All right, so let's come over here. F of 2.1, so it'd be 2.1 squared minus 5 times 2.1 minus 6. What do we got there? I get negative 12.09. f of 2, well, plug in the 2, you got 4 plus 10 minus 6, that's, oh, that's 0. Is that 0? Seems a little, try. Drop 1, 0. Okay. All right. dy is f prime of x times dx. So dy is going to be here, f prime, so I do derivative of this, 2x plus 5. So dy is going to be 2x plus 5 times dx, which in this case would be the x is 2, so that would be 4 plus 5 times my dx is a given. But good news is dx is the same as delta x. So if delta x is 0.1, then dx is also 0.1. That's going to be 0.9. And that's why I'm thinking this. What did I do wrong here? Did something wrong. Oh, this wasn't wrong. This is wrong. That's not 0. 8, that's 14 minus, that's 8. That's still exactly what I... Here's what I did. Let's start this one. You guys are supposed to help me out here. All right. F of 2.1. It's 2.1 squared plus 5 times 2.1 minus 6. I did a minus instead of plus there. That's just something on the looking right there. Okay, so 2.1 squared plus 5 times 2.1 minus 6. 8.9, there we go. 8.91 minus f of 2, that was 8. Yeah, 2 squared minus 10 plus minus. Okay. Yeah, that's it. That's 0.9. I'm much better with that. All right, so delta y is 0.91 and dy is 0.9. Now, let's graph this scenario here and label all the pieces, dy, delta y, dx, and delta x. So I want to graph this little scenario here. Well, what that means is I want to graph the function and the tangent line, and then I can label, okay? So x squared plus 5x minus 6 and I'm looking at x equals 2, so I might want to zoom in here to a little bit maybe that's too far. Let's make it -5 or +5. So maybe even further out than that. Just something that gives us kind of a, may have to go a little more on the y-axis. Yeah, because at x equals 2, I'm up here at 8, right? My best choice there. All right. So do something like this. So I'm looking at this x equals 2 value, so that's where I want the graph there. Now the dy, the delta y, well, dx and dy, those depend on the tangent line. So you just kind of sketch in here your tangent line as well. So that this is the function value, function graph. And so I also went in to do the tangent line, which that's going to be fun to draw in here, but yeah, so that's going to be the tangent line at 2. So what this is saying, if I go, so my delta x is 0.1. So if I go out to 0.1, which is not too far out there, so at 2.1, the let's still hit get rid of this so I can focus down on this. I made a mess of this one. Okay, so the tangent line, it goes off. It's up here. That's where it's tangent. Here's what it is. So if I go up to this point, it's that, and then at that point, 2.1 is not very far over, and so I've got a little bit of a kind of a triangular setup there. This is the curve, and then the tangent line's on the outside here. So it's a little different than the one I started with, because, you know, dy over dx, that's the rise over the run for the tangent line. And so in this case, here's the tangent line, so this is the run, so this is dx right here. And that's the rise for the tangent line, so that's dy. That's what dy and dx are. They're the rise and the run of the tangent line. Delta x and delta y, well, really delta x and dx are the same, so you got dx, you got delta x. But then what about delta y? Well, delta y is the change in the y values. So that's from the y value here up to the y value here. And so on my graph here, dy just goes up to here. This would be delta y though, because it goes from one point to another point on the graph, which the graph is the inside one here. The tangent line's on the outside. So anyway, you just kind of have to figure out the dx and the dy, those are on the tangent line, rise and run. And then the delta y, you know, delta x is the same as dx, but then the delta y is from one point on the graph to the other point on the graph, the change on the y values a bit, so anyway.